So now I would like to introduce you the continuity equation in cylindrical or polar coordinates. So again, it is actually showing you the same thing. So we need to calculate the mass flow rate for the inlet for every axis. So but in polar coordinates, so the axis is quite different because we have an r axis which is parallel with the radius. So and then we have a tangent mean parallel with the rotational direction, and also the z means the axis of that one. So this element is actually come from the part of this one. So it will taken out and it will looks like this one. So and then this is the direction. The z direction is actually the uh, normal to the screen, or it can be shown like this one. And the r direction is for radial, and then the theta is actually the tangent for this contact point. So it will reflect the angle, the theta here. So this is the simplification of this diagram from this diagram. Okay, again, so it's used the idea of this one. Mass flow rate at inlet is minus mass flow rate at outlet equal to dm dt, mean the mass changes inside the system. So and then if you do this, you could have all this one. So for example, if we so I do this for one by one because if not, we will have a long equation. So that's not good. Maybe we do simple mistake. So we go for the r direction first. So and then mass flow rate inlet minus mass flow rate outlet. So if you do this, you will get this one. So and then here, if you have a double multiplication like this for dr times dr, so you could assume it is too small. So you could neglect the value of this item. So this is the simplification, the assumption that we need to use. So this is the mass flow rate for z direction. So you could do this. The z direction means this is the inlet and this is the outlet. Okay, you could say that this is the rho, this is the Vz, and r dr d theta. You know that the r d theta means the length of the length of this one, and dr is actually the length of this one. So we assume that this length is actually almost same with this one, so we simplify it, we just use this length. So means that the r d theta and dr is actually showing the area of this one. Okay, so means that we know that mass m dot is rho av. So the a here is actually this one. So mean we take r d theta dr as the cross-sectional area. So if we do this, so we will get this term. So and then we do we will get this term, and then we calculate the mass flow rate for the theta direction. So we will get this one. And then the fourth, we calculate the mass. Mass is rho times volume. And we know the volume is r d theta dr dz. So this is dz. So this is dr, and this is r d theta. So we multiply all this length, so we could get the volume of this cube. So and then we put into the m here. So we have the m dt of this one. So and then this is our basic equation. We substitute everything, and then we have this one. And again, as I said, please make sure that you know to do the differential equation. You know to do the differential derivation here. So if we have del over dt for rho and r, we could split it into rho dr dt plus r d rho dt. So here again, please make sure that you know to read, you understand the meaning of each equation. So for example, here dr dt means the changes of radius along the time. So according to this diagram, we found that the radius is not increased. So mean the value of dr dt is actually not is equal to 0. It's not exist. So we need to eliminate the amount, the value of dr dt. So we eliminate this R because there are no changes of R regarding to the times. Okay, you need to understand the mathematical terms. So and then we could simplify it like this one. So this is uh, the continuity equation for the compressible equation of continuity. Okay, so what is the difference between the compressible and incompressible? It is actually you need to do something with the density. So I will show you here. So for 2D incompressible, there is no, okay, so here, I'm sorry, okay. This is for the compressible equation. So compressible equations means that the amount of density need to be taken into account, because compressible means the density keep changing. Might be it is increase or decrease. Okay, this is the idea of compressible. However, normally, in fluid mechanics, we are use liquid as our medium. We use water. So water is categorized as incompressible. For incompressible, we found that there are no changes in density. So means we could simplify it. So and then we could neglect the value of rho. Okay, means that the rho is not changed. And then if you are doing two-dimensional, you can neglect the value of z direction. So mean the continuity equation will become like this. Okay, so and then sometime in certain textbook, they will give you different symbol for polar coordinate. Sometimes they use VR and V theta, and sometimes they use U prime and V prime. So this is actually the way people write the symbol. So and then this is the simplification, means this is the continuity for Cartesian coordinate, and this is the continuity for polar coordinates. Okay, and then so this is the Navier-Stokes again for polar coordinates. So this is the simple the explanation, the extension about d over dt and nabla. So this is for r axis. Again, I remind you here, the equation for r axis, theta axis, and z axis is not the same for polar coordinate. So this is for r, this is for theta, and this is for z axis. And this is what I show you. Sometimes in certain textbook, they convert the value of this one into this value.